Okay, so as you can see on the screen, we're going to be looking at a concept called the central limit theorem here in our data science class. Now, this is the semester of COVID-19 social distancing. This topic, I usually have it lumped together with a topic called sampling distributions. However, sampling distributions, for folks who haven't taken a bunch of statistics classes like I have, is usually difficult to grasp. And over the years, I've had a nice in class activity that would help us understand what's going on. However, with social distancing, we cannot run the activity today. So, admittedly, I am going to try to explain the main points or ideas from the sampling distributions, and then we'll go into the calculations for the central limit theorem instead. The main idea is that what tends to happen in practice when we're conducting science is that we study a relatively small sample to understand a larger population. Now, here in our course, we have studied formulas such as mean, median, standard deviation, etc. And the question that would come up is that which calculations or formulas from a done on a sample are still valid when we're describing the larger population? Is it okay for us to make that transition? And what happens in the background is that some of these processes actually introduce bias when we're going from the sample to the population. So, for example, early in the semester, we talked about variance. That was that process where we take data, subtract by the mean, square all the numbers, add up all the numbers. And at that point, you would think you would divide by however many numbers there are. Let's represent that by capital N here. But skipping ahead in the story, what happens is that if you do this version of the formula on a relatively small sample, and you're trying to describe the variance, how spread apart the numbers usually are for the much larger population, the result would underestimate what should happen for the true population variance. So, skipping a lot of math theory, what the mathematicians and engineers did were to adjust the formula. It turns out after a bunch of work, the adjustment that was needed was to actually divide by n minus 1 instead. This is in the literature called Bessel's correction, after an engineer named Bessel. And thus, using this formula called the sample variance, the one we're labeling s squared, we could go from the relatively small sample to a much larger population without underestimating, without introducing bias into our calculation. So this is finally why we would want to divide by n minus 1 in the first place. Now, for our purposes here in data science in our Bio 18 course, the unbiased estimators, as you suspect, those are the ones that do not introduce bias going from the sample to the population. The unbiased estimators include the sample mean x bar, the s squared that has this n minus 1 in the denominator, and proportions as well. And just to finally finish off, what I wanted to say in the topic that was left out because we're not meeting in person is that some more example of biased estimators include the sample median and the sample standard deviation S. But when we talk about standard deviations, it's usually considered, loosely speaking, okay in practice because the discrepancy between the sample standard deviation and the true population standard deviation is usually so small that we could use them almost interchangeably without much concern. And the reason why I bring up this material in a haphazard way here in the semester is just because we need to know that it's still okay to use the sample mean and the sample standard deviation as we move forward to the last month's worth of material. I'm going to take a break here to see if there are any questions from the folks in the chat room. Alright, so what would happen here in the semester after this strange interlude into this notion of estimators and sampling distributions is that then we could move into the central limit theorem. In words, what the central limit theorem says is that as the sample size n increases, the variance in the distribution decreases. That is, I don't have a diagram in front of us, but for the bell curve actually gets skinnier, and that affects the calculations. The bell curve gets skinnier as we get more and more data as n increases. The jargon is that our treatment of the standard deviation, sigma, becomes the standard error. That is, this sigma is adjusted to become sigma over the square root of n. And since we've seen sigma in the z-score conversion formula, that gets adjusted, so this denominator down here in the bottom right is now the standard error, sigma over the square root of n. We'll run this through an example. Admittedly, this example is quite old-fashioned, several decades old, but nevertheless, I like the wording of it because it's a little easy to grasp on the wording. Reading off the example. We're going to use this information about overhead reach distances of adult females. The average was 205.5 centimeters with a standard deviation of 8.6 centimeters. And the overhead reach distances are normally distributed. The overhead reach distances are used in planning assembly workstations. That is for people who are working in offices and they have shelves or storage above their desk. The workspaces were designed for women because at the time such employees were mainly women, and moreover, you did not want to discriminate against women. So the focus was on women there. And they were saying the overhead reach distances where it was comfortable to reach for something without having to get up out of your chair. So now reading our task here in part A, if one adult female is randomly selected, find the probability that her overhead reach distance is less than 222.7 centimeters. So we're going to use the normal distribution, the bell curve once again, assuming kind of in the background that it was okay to do so in the first place. Let's see, I have the work somewhere here. So similar to what we were doing last week, we're going to set our random variable x less than 222.7, because that's the wording here, less than 222.7. The area we would shade under the bell curve would be our probability. And the way we write that area under the curve in math notation is with this capital phi function here. That is, mathematically speaking, kind of skipping the notion of an integral, and we want to plug in numbers into what's called the cumulative distribution function. For the normal distribution, the cumulative distribution function is labeled capital phi. But moreover, notice how I'm plugging in the numbers. We are concerned about this location, 222.7. We were given a mean of mu equals 205.5 and a sigma, a standard deviation, of 8.6. So the 205 goes here in the top right corner. The 8.6 goes here in the denominator. And if nothing else, by process of elimination, the 222.7 is here in the top left of this fraction. That's our data value for x. Now, even if we had several semesters of calculus under our belts, the calculation would be tedious to do by hand. So we're going to focus on our software abilities. We're going to type this into RStudio. Finding the probability from a normal distribution, we'll once again import a p-norm function. And we'll here get a probability of about 98%. I'll bring that back right back in a second here. So in other words, what I have on the PDF right in front of you is how we would set up the problem. And then what I have up here in RStudio is how we would finish the problem. $205.5. Thank you to the folks in chat. That changes this number. So there we go. Thank you for finding that typo of mine. Alright, so now we'll move down to part B, where I have a phrasing that's slightly more complicated. If 49 adult females are randomly selected, what is the probability that they have a mean overhead reach That's less than 207 centimeters. So we're going to have 49 women and ask for their average overhead reach distance. How are they as a collective? In particular, in the notation, whoops, our value for n is 49. And what the central limit theorem said in the above formulas is that we'll be using this updated version of the z-score conversion, the one with the square root of n down here. I think I got the typos there. Matching up the wording with the notation, mean overhead reach, the word mean is synonymous with average, and notation wise, that's x bar. Less than 207, that's expressed by this inequality here. And then to handle the notions of calculating a probability as an area under the bell curve, we plug in these numbers into our phi function. So now the adjustment that's made in RStudio is that square root of n. So you'll notice compared to the previous example, we have this adjustment here. Let me go ahead and type that number into the PDF. And I'll take a break here to see if there are any questions from the folks in chat. Alright, so next I have a couple more examples with the same setting, the overhead reach distances, but just to give you some more examples of slightly different phrasing. In part C, I'm asking if one adult female is randomly selected, find the probability that her overhead reach is greater than 195 centimeters. So this time around, setting x greater than 195. The way to compensate for how the inequality is actually going in the opposite direction than it was in the previous example is to take the complement, 1 minus 5. Or, in other words, because the wording is greater than instead of less than, we're going to use the 1 minus 5 complement. See how this plays out in RStudio. We use a pnorm function again. Be sure to one way or the other use the complement. And we'll have this result here, which I think was just a coincidence with part B. All right, now in part D, the changes that I'm asking if 25 adult females are randomly selected, that is more than one. Find the probability that they have a mean overhead reach distance greater than 203. So here the word mean is expressed by this x bar. Greater than 203 centimeters is expressed by this inequality. To reverse the inequality, once again, we'll employ the complement 1 minus 5. And since we have a group of 25 people, n equals 25, and we use the updated version of our z-score conversion with the square root of n. We make a similar adjustment when we type in the code into RStudio with the square root of 25 here at the right side. And we'll get an answer of about 93%. I'll go ahead and take a break here to see what questions you might have at this moment. All right, so we'll go ahead and move on to a much more modern example. My usual cravings for In-N-Out hamburgers. Reading off the example, the average serving size for an In-N-Out hamburger with onions is 243 grams. Suppose that the company has a restaurant employee prepare 35 hamburgers. If the population standard deviation for the serving size is 44 grams, what is the probability that the mean serving size is less than 230? So this is a quality control situation. We're simulating the process where an inspector comes by, their own company inspector, and is making sure that the hamburgers are not too small. So we'll parse the information. The mean was 243, so that'll coordinate with mu. The standard deviation was given as 44 grams, so that will be sigma. And the amount of items that we're studying, that will be the 35 hamburgers, so n equals 35. Whoops, I have a typo here. Let me fix that. So we're asking what's the probability that on average of a batch of hamburgers, their mean size is less than 230 grams. Because we have multiple hamburgers, we'll use our updated z-score formula, the one with square root of n, and plug in the numbers as such to take care of the notions of area under the curve. because the inequality was less than, we do not need the 1 minus complement here. But because we are examining multiple items together, namely the 35 hamburgers, we need to have the adjustment with the square root of 35 here. Admittedly, today is going to be a really short lecture because we did not have a classroom activity, in-person classroom activity today. What I want to do just for a few minutes is to go over some code that I have also uploaded for my students. The overall concept is called sample distributions. And looking at to play devil's advocate, looking at this version of the variance formula, the one was just n in the denominator. The scientists say that's a biased estimate when moving from the sample to the population. What this code does is generates 18 random numbers between 0 and 1. That's what the runif function does. Generates a random number between 0 and 1. And here I'm generating 18 of them. And I'm going to call that one sample of 18 numbers. Now, I didn't develop all the math theory in front of you, but it turns out in this situation, sigma squared is 1/12. The true variance in the background theory is 1/12. So we're going to do a simulation where we're generating those 18 random numbers, and we're doing that 10,000 times. We're going to run each group of 18 numbers in what I'm calling the bad version of the variance formula. The one with just an n in this denominator. And then finally, we're going to graph that. So when we grab 18 numbers at a time and take the variance of those, we're doing that over and over again. And this blue curve here, that's what's called the sampling distribution. Long story short, the true answer for the situation was supposed to be 1/12, which is represented by this red vertical line. However, there's a bit of a shift. The blue hill, that curve, does not seem to line up completely well with the red vertical line. The question in chat is, could you have the R code? And this document here, the one I'm showing you right now, has already been uploaded to our CAT courses page. So reading off this sentence here, since the sample distribution does not line up with the population variance, we say that sigma squared is a biased estimator going from the sample to the population. Oh, and I should mention the one of the reasons why this code is pertinent is because I'm asking you to do something similar in the RH3 homework assignment. So for those folks who are doing the RH3 homework assignment due next Friday, you would need this code here. So now that I've shown you an example of a biased estimator, we'll do an example of one that is unbiased. Very similar setup, except that this denominator in this formula in the middle of the page, this denominator is n minus 1. With that adjustment, this denominator being n minus 1, I'm going to call this the good variance formula. We're going to run through the simulation again, grabbing 18 numbers at a time, running it through the good variance formula, and then doing that 10,000 times. The simulation is collected in this blue curve, and where the true answer should be is represented by this red vertical line. Loosely speaking, in the sense that I simply ran this through a computer program over and over again. Empirically, we have shown that the blue curve lines up with the red line much better this time around. And in words in the technical jargon, since the sampling distribution lines up with the true population variance, we say that the sample variance S squared is unbiased. So that's actually going to draw today's lecture to a close. I know, especially for these end of semester materials that are higher level concepts, this delivery I'm doing right now is not quite efficient, but we're going to try to get through the semester as easily and as smoothly as we can. So, to my students, please continue to send me emails about what's confusing or whatnot, and we'll see if we could finish this semester well. That's going to be it for today, and I'll end the video here and say I'll see you next time.